monitor recording. Okay, so today we are going to jump to section 7.9 in the book. So hopefully you skim through that section a little bit just to get a little preview, right? You might be asking, it wasn't even yesterday, last week, right? We cover up to section 7.3 on digital gates, right? And now I'm jumping to section 7.9. And the reason for that is that I think it just makes more sense, at least to me, to jump into this because, right, the last thing we learned about binary numbers is to how to add and subtract them, right? Adding is just, subtracting is just adding negative numbers, right? And 7.9 is going to basically teach you how your computer actually add things physically with electronic gates, okay? Because there isn't like an adder gate, right, or a subtraction gate, right? So there's going to be a combination of AND gates, not gates, and XOR gates, and all that stuff that's going to do this addition for us. And I'm going to see how this happens, okay? So going back, reviewing, right? So if we're adding two numbers together, right, in binary, or even in decimal, right? We put them in this, we go back to elementary schools and then we put, the first number in one row and then the second number in another row, and then we just add column by column, right? So, right, so here you got 1 plus 0 equals to 1, and then 0 plus 0 equals to 1, right? So 1 plus 0, right? Right, that's indeed equal to 1, and the answer is correct, right? But then if we add 1 plus 1, right, 1 plus 1 here has a 0 here, right? But then has a carry of 1, and that carry of 1 carries down, plus 1 plus 0 is 1, right? So there's two things you're doing here, right? You have now we're going to think about electronics, right? You have your inputs here, right? And you have your outputs here, right? And so what we're going to do is going to try to figure out how we can do this on a logic gate instead. Okay, so I'm just going to go back up to, okay, so, right, so 1 plus 0 should be 1, right? But also like 0 plus 1 should be 1 also, right? But 0 plus 0 should be 0. 1 plus 1 is equal to 0. Okay, so I'm going to write this out over here. Okay, so let's say my A is this, B is this. So this is maybe like my A row, my B row, right? And this is my Q for my output, right? So what we want is that 0, 0 gives you a 0 as an output, 1, 0 gives you a 1 as an output, 0, 1 gives you a 1 as an output, 1, 1 gives you a 0 as an output. Okay? Can you guys think about any logic gates that we learned so far to figure out what that is? I'm sorry? An XOR gate. Yeah, so don't peek below. Okay? So this is basically the operation of an XOR gate. Okay? Okay? So figuring out what this number is an XOR operation. Okay? So we can put an XOR here. Okay? So, but then there's also this carry number that we have to figure out all the time, right? In case there's a 1, 1, right? What operation only gives you a 1 when there's 1, 1 as an input? An AND gate, right? So this is an AND operation. So a combination of XOR and an AND should be able to add things for you. And this is exactly what we're going to do down here. Okay? So these are known as half adders. We're going to see why it's called half adder as opposed to a full adder, right? So you have an input bit here, 0, 1, input bit here, 0, 1. So this corresponds, right, to, one bit of each of the number, right? So for example, if I'm trying to add 3 plus 3, right, that's in binary, right? That's equivalent to 1, 1 plus 1, 1, right? This A here corresponds to this bit. This B here corresponds to this bit only. Okay, we're not even dealing with the second bit yet, right? Okay. Okay. So, right, by putting in A and B into an exclusive OR gate, we calculate, right? Let's go back up here, right? We calculate what this is, right? In the logic realm, right? We call that Q, right? What we're gonna do, we're gonna call this LSB now, or like a lot of times just L. Okay, LSB stands for the least significant bit because we're gonna be dealing with the least significant bit over here on the right-hand side. Okay. And the AND gate output is going to be the carry. Notice that both A and B are connected to the AND gate because these dotted line indicates the wire are connected to each other. Okay. In fact, right, this is symbolized with this kind of like a box diagram as a, sorry, it's called a functional diagram. I just kind of covered it. Sorry about that. Right. This functional diagram. Right, and you just put a box, and then you put 1/2 add. That signifies a half adder, and that has 2 inputs and 2 outputs. Okay, right. The A and B are the inputs. The L is one of the outputs, and then the C for the carry is the other output. Okay, right. So let's see how this works. Okay, so right, let's have this up here. Let's say I'm adding 3 plus 3. Okay. So we're going to need actually 2 of these in order to do this operation because we're going to have to deal with 2 bits, right? So let's see if it works out that way, okay? So what I'm going to do, so this is the A row and then the B row, okay? And this is the ones place, this is the twos place here, right? Okay? The ones place, I'm going to call this, I'm going to translate this to basically like a vector. Yeah, vectors are okay, right? I can talk about vector. Right, as 1, 1, right? Because those are both ones right there. Okay. Okay. What I'm going to do is I'm going to actually even signify this as A0, A1. Okay. So be a little careful. Things that flip, right? This number corresponds to this number. This number corresponds to this number, right? Okay. So this is actually here. I'm going to highlight the same color here. This is usually what confuses a lot of people. Right, this is the ones place, this is the twos place, right? And then this can keep going, right, to the fours place, the eights place, and stuff like that, right? We're just going to limit it to to 2 bits for now, just for this calculation. Okay. Therefore, right, B is also going to be 1, 1. It's a little confusing because this, all these ones around look the same, but they're representing different variables, right? Okay. So, right, if we put let's see, this is going to be B0, B1. Oops. Did I do that right? Yeah, B1. Okay. If I put in, let's see, go over here. This number here is A0. This is B0. This is A1, B1, right? Okay. So if I put in A0 here and A0 here, right? I take the OR, XOR between them, right? That should give me a 0 as the output, right? XOR between 1, 1 is 0. And that is indeed what I get, okay? Right? And then, but A0, B0 also go into the AND gate, which is what's going to connect to the carry of this, okay? There's a lot of arrows going around, unfortunately, right? And that indeed does give me 1, okay? Okay? If I, have some magical power that allows me to use the same half adder once again, right? If I take it to here, okay, what happened is that, right, A1 can be reused again, right? Instead of using the 0, I'm just going to go to 1, right? The XOR between 1, 1 should be 0, right? But we want a 1 there, right? So there's a modification we have to do now, okay? And this is why these are called half adders as opposed to full adder, because we need to add something to it in order to complete the operation, okay? So what we need to do to add 2 bits plus 2 bits is actually we're going to need, how many, do you guys want to guess? How many half adders? So 1 half adder does not exactly add 1 bit, right? You need at least 2 half adders who seems to add 1 bit. How many half adder do you think it'll be needed to add 2 bits? You would think 4, right? Why? You're cheating. You're looking ahead. It's actually not 4 because you don't. It's a half adder plus an OR gate that in addition you need. Okay, so let's see. Let me see if I can draw this properly. So you get an XOR gate. I'm just copying the half adders from the up top up here, right? Right. So I'm gonna do. I'm gonna pipe in the A0 input here, B0 input here. Okay, and then there's an AND gate underneath it, right? That's connected the same way, right? Okay. Okay. And then I'm going to line up another half adder here, right? XOR gate. And instead of inputting A0 and A1, sorry, A0 and B0, right, I'm going to put in A1 and B1 as the input here, right? Because that's the twos place that I'm putting in. So this is the ones place. This is the twos place. Okay? Right? Similarly, I'm going to connect these to the AND so that we can actually have the carry out, right? Okay? And then as Matthew cheated and then looked ahead, it's going to need one more. So to do 2 bits, you need not 4, but actually 3 half adders. So we're going to place another third one halfway between these guys. Okay? And I'm going to have to connect them together in a special way so that the places gets placed correctly. Okay? So as we saw from this example up here, right? The ones place answer, right, is correct, right? So that's actually directly from the output here. Okay? We're going to call that L0. Okay? Right? The carry out does not give you the right answer, right? What we're going to do is we're going to pipe that into the first input of the second half adder. Okay? Okay? Then what we're going to do is we're going to have what the heck's going on here? We're going to have this going out to the input of the the third XOR gate. In fact, we're going to make one more connection here. We're going to bring this and share this with this. And then we're going to share this with this. Okay? And then all of this is going to get wrapped up together. And we're going to have to figure out what gate to put at the end here. Okay? We're not sure what that is yet. Okay? So these XOR gates, right, the next bit output should be L1, okay? Right? The last output here should be L2, right? Because when you add two 2-bit number together, the answer could be 3 bits, right? Okay? So that's where this carry failed us, right? The single half adder failed us to do that. That's why we need to configure it like this. Okay? So let's see how if this works at all, right? So as we saw, 0 plus 0 gives you 0, right? 1, 0 gives you 1, which is what you want. 0, 1 gives you 1, right? 1, 1 should give you 0, which is exactly what we want. So L0 is good to go, right? Right? Everybody agrees? Okay. Let's see what's the result for L1, okay? Right? L1 is the thing that kind of clumps everything together, right? It depends on all 4 of these things, okay? Right? So let's do this addition here, right? So we're going to have A0 is 1, B0 is 1, A1 is 1, B1 is 1, right? So all ones, right? We want the answer to be 1, okay? Let's see if that's true, okay? So the AND between 1, 1 should be 1 as the output here, right? Let's put intermediate here, right? Okay? And then the XOR between 1 and 1 should be what? 0, right? Right? So now, right, these come together. The XOR between 1, 0 should give you what? Should give you 1. So this does work, at least in this case, right? And I'll let you check the other 15 cases, okay? Because there's actually 4 different combinations you can set up here, right? But it does work for our calculation right now. The last thing we have to figure out is what type of gate to put here in order to basically get an output that makes sense for L2, right? Right? L2, right, is basically the carry of the ones place, right? So whatever carries up here, you want it to get up there. Okay? So when all of these are ones, right, you want this output to be 1, okay? Right? So what happened here is that, right, we already figured out what the output from this two things are, right? This is 1, and this is 1 going to this AND gate here, right? That should give you a 0 as an output, right? Okay. Okay. So the AND gate here gives you a 1 as the output, right? And you want a 1 on the other side, okay? In fact, you want a 1 on the other side no matter if it's 0, 1, 1, 0, or 1, 1, okay? What type of gate would that be? Just a regular OR, yeah, not an exclusive OR, okay? Okay, and that's what gives you the 3-bit output that you want, okay? So all of this you can figure out by just, drawing a bunch of gates, okay? In fact, right, we can go to the functional diagram version of this, right? Draw a box around this, right? This is our first half adder, right? Draw a box around this. This is our second half adder. Draw a box around this. This is our third half adder. And then an additional, you have to add an OR gate at the end. And that's it. 3 half adders and an OR gives you 2-bit by 2-bit addition. Okay? 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 And here's the functional diagram drawn nicely in the textbook. And this is probably where you saw the answer. Right? Okay? All right. So if we want to add 2 bits by 2 bits, right? Sorry. If we want to add 3 bits together, let's just do one more, okay? Because it's going to take a while if I have to draw the 4 bits by 4 bits, right? When you add 3 bits number together, instead of 2 bits on each numbers, you have 3 bits on each number, right? So there's going to be an A0, A1, and A2, right? So let's have this written down, all right? A0, A1, A2, right? And then the second input, right, is going to be the B's, right? Oops, B1, B2, right? And the pattern, you can start to see the pattern here. And those of you who ever looked at the Pascal triangle, remember what Pascal triangle is, right? To figure out the coefficients of binomials? No, okay. Not a lot of people do that every day. Okay. It's going to start to look familiar, right? So these input, all of these input goes into half adder inputs, right? Half adder, half adder, half adders. Okay. Between each of the half adder, there has to be another half adder, right, to deal with the carryout. Okay. So we're going to draw a half adder between them, right? Okay. And this goes here, this goes here, and then there's one line that kind of goes along the bottom. Okay. Right. These are also half adders. Since there are two half adders, you need another half adder between them, okay, to combine these outputs, okay? And you can see now why people call these Pascal triangle, right? This L0, this will be L1, this will be, okay, this will be L3, right? It is, right? Sorry, oh yeah, I can't count. Well, L1, L2, okay? And then on the bottom here, now you have 3 different inputs. Okay, and remember that digital gates not necessarily only have 2 inputs, it can have 3 input, right? And you just basically OR all 3 of these things to get L3. Okay, and this is a half adder, of course. Okay, hopefully you guys remember. Now it looks like a triangle, right? In fact, the book does the 4-bit version for you in a much nicer diagram. Instead of calling them L's, they call them O's, right? O for outputs, right? So if you add 2 4-bit numbers together, you could end up with a 5-bit number. Okay? All right. So let's do a little analysis on, how many gates does it take to add, maybe like, if you want to add n-bit number together, right? So like 4 bits plus 4 bits, 6 bits plus 6 bits, 7 bits plus 7 bits, right? And then let's call n the number of half adders, right? Right? The number of half adders you need is, first of all, you need the first row here. The second row has 1 fewer. The third row has 1 fewer. The next row has one fewer until you get to 1, right? Hopefully that makes sense. Right? 4, 3, 2, 1, right? Every row gets 1 less. Okay? Those of you who are in math or had maths or in maths, I don't know if you deal with series, okay? You can actually convert this. This is going to be equivalent to n squared, right? You just have all these n's together, right? Minus, it's going to be a little bit less than n squared, minus the sum over all the m's, where m is how many columns you make, okay? Okay, right? So the number of half adders you need grows as n squared, right? So if you're dealing with 4 bits, right, it's going to be 16 half adder minus a little bit of something, right? If you're dealing with 64-bit addition, it's 64 square minus some number, okay? I'm not sure what 64 square is, right? So that's 2 to the 8 squared to the 16. It's a big number, okay? It's like 65,000 or something like that, okay? So you can see that, right? Having the number of adders grow as the number of bits square is not a good scaling, okay? Your stuff is going to get more and more expensive, okay? Okay. So this implementation is very simple and logical, right? All we did is we looked at our how to add numbers up on columns and rows, right, from first grade, and then yeah, we just did that, okay? Okay. But it's not scalable, meaning it doesn't scale well if you go up a higher number of bits, okay? And this is why people actually use this thing called full adders, okay? A full adder is basically 2 half adders combined together with an OR gate that's already built into it, okay? Right? So, this is a half adder, this is a half adder, and then you have the OR gate that's there all the time already, okay? All right. So I'm not going to go through the logic on how this gets constructed, but you can check a few of these, right? So let's say, right, if you add, so there's one more thing that's a little bit different about the full adder, right? Instead of just 2 inputs, it's actually 3 inputs, okay? The third input allows you to have the carry in number or not, but at the ones place, the carry in should be 0. Okay, because you're not carrying in the negative ones place, whatever that is, right? Okay, so let's say, right, my A and B are 0, my carry in is 0, right? I expect the result 0 plus 0 should be 0 with no carry, right? Okay, so let's go through that exercise just once just to see what happens, right? If I set this number over here to be 0, 0, 0, right? I am hoping that this will give me the correct result. Okay, this is once again like a truth table checking, right? Instead of just logic gates, now we have this full adder logic, right? Right. So if we put in A and B as 0, this XOR gate should give us 0 here, right? 0. The AND between 0 and 0 is also 0. Okay, right? And then the XOR, right, from 0 up here, and then 0 through here, right, it's also 0. So that checks out. The L is correct, right? Right? Okay. And then, right, since everything is 0, right, the AND between 0 and 0 is also 0. And then the XOR between 0 and 0 is also 0, right? So the carry out is also correct. All right, let's just do one more. Okay, we're not going to do all. Let's just pick a random row, right? Let's do one with carry out. Let's do this one. Okay, one where A is 1, B is 0, C is 1. Okay, so we're going to make this 1. Okay, the answer we expect, right, which is out here, right, is 1, 0. Okay, 1, 0. Right. All right. Let's see what happens. Okay, let's erase all the stuff in between. Okay, so, right, the XOR between A and B here, right, should be 1. The AND gate here should be 0, right? The XOR between 1 and 1 should be 0. Okay, oops. do that right? The XOR, yeah, that should be 1. This should be 0. Oh yeah, okay. And then, right, this AND gate here, right, comes from up here all the way down to here, which is all 1. And this one comes from down here. This is also 1. The AND between 1 and 1 is going to give you a 1, right? And therefore, the regular OR gate between 1 and 1 should give you a 1 as the output. Okay? So at least we checked this one. We checked this one. Oops, I didn't even point to the right place, of course. Right? Okay? And you guys can check the rest if you want. I don't know if I put down the homework or not. Maybe I should. Okay? I think it's good to go through this flow logic. Okay? Yeah? No? No? Yeah. Yeah, each full adder gives you 1 bit. So if you want to add 10 bits together, you need 10 full adders. Okay? Right? Because I only deal with, we're not dealing with the vector version of this, right? So exactly as Shane just asked, right? If you want to add more bits, you chain up the full adders together, right? So you got A1, B, you got the ones place, the twos place, the fours place, the eights place, right? And that allowed you to add up multiple bits, okay? The important thing is that whatever carry out comes out of the previous bit has to be connected to the carry in of the next bit, okay? Right? And this first bit here, right, we're just going to connect it to ground because we expect it to be 0, right? Okay? Okay. So you may think, well, there's a lot of stuff in these full adders though, right? Right? It's actually every full adder, takes twice as many parts, right, as a half adder, right? That's why they're called half adders, right? So full adder costs twice as much as a half adder, okay? But the full adder scales a lot better because, right, basically the number of bits you're dealing with, right, is equal to the number of full adders, right? So for example, if you're doing 4-bit plus 4-bit addition, right, if you're doing this with half adders, right, it's gonna take 10 half adders, okay? Because it's gonna be 16 minus some numbers, okay? We did this calculation. And in total, that's gonna take about 23 gates, okay? If you're doing the same thing with full adders, it's actually gonna only take you 20 gates, okay? So already at 4 bits, anything, so 3 bits is actually more efficient to do with half adders. 4 bits is when it breaks over to full adders being better already. Okay? So if you're doing any addition beyond 3 bits, if you want to add a number higher than 7, right? Then you might as well just use full adders. Okay? So that's why people, I think the half adder is a good teaching tool, right? It's just line up the rows and then add up the stuff, right? But it's basically full adders is how you would make circuits. Okay. All right. Sorry, how you would do computation in any electronic systems. Okay. So so this is basically the same circuit as above, right? Where you have 2 XORs, 2 ANDs, and an OR gate. Okay. The thing I want to highlight out here is that, right? Let's count how many wires this requires, okay? So you need a wire from ground to this XOR gate, and you need a wire between these two guys, right? There's 2, let's count, right? Right? You have a wire here for your input, right? You have a wire to the AND, right? And then the B input also has two, two wires, right? You have a wire between here and here, right? And that's 9 wires already. We have a wire between here, 10 wires, okay? And you have the wire between the AND gate and the OR gate, 11 wires. And of course you have wires to the output, right? You have 13 wires, okay, to build a single full adder, okay? Right? And that doesn't include the power and the ground bus, right? So that's going to add like, another 6 wires to things, okay? So you actually have 9 wires in order to do 1-bit addition, Okay, if you want to do 64-bit by 64-bit addition, right, that's about 1200 wires. Okay, do you want to do that on your breadboard? Okay. This is where we're going to start introducing you to this idea called FPGA. So they're called field programmable gate array. But right, these wires, right, it doesn't necessarily have to be on the breadboard, right? Maybe you can design a integrated circuit that does adding for you, right? And you just have the wire permanently built in there. Okay. Since these wires are going to be permanently inside that chip, you cannot change it, right? Okay. So these are known as application specific standard products, ASSP, ASP. Okay. And sometimes they just call it ASP without the standard. Um, and these are like designed specifically for one task. For example, in high energy physics, they use that a lot for data processing because you want something to be really fast, right? And you know exactly what the computation has to be. It has to add two numbers together, right? Whatever that is, right? It has to add two 12-bits numbers together all the time. It just does that over and over and over again. You can design just a chip for that, okay? Um, in our class, right, instead of designing the chip and then sending off to some wafer factory to have it laid out, right, what we're going to do is we're going to teach you guys how to use these things called field programmable gate arrays. In fact, I think it's module 8, right, it has a little bit of an introduction to it. There's a little PDF that I posted. Okay, and there's going to be a second PDF on how to deal with programming these FPGAs for the week 9. So really make sure you read those modules, read those PDFs before the lecture, and therefore you get a little preview and kind of get get what the answer is beforehand. Okay. Okay. The idea of FPGA is pretty simple, actually, right? So let's say instead of sticking in particular gates, right, and then connecting the wires between them one at a time. What I'm going to do is I'm going to put a bunch of gates in a two-dimensional array, just like on a breadboard. I'm going to have wires coming out of these gates, okay, right, both on the output and on some on the inputs, and then some on both, right? Just a bunch of wires going around, okay? These wires, these green wires, are not connected to each other, okay? All right. What I can do is I can make it so that if I physically, this is actually how this was first invented. So this is on a board where you have the two wires basically kind of close to each other. But if you stick a little chopstick in there or something like that, you push the wire into each other so they're connected. Okay, and of course we're not going to do this today because there's going to need like 32,000 chopsticks. Okay, if you do this on the BASIS board that you have on your table right now. Okay, so let's see if we can replicate our full adder using this. Okay, in fact, we can do a 2-bit full adder here, right? So, right, the input for the full adders, right? Remember, we're trying to add two numbers together, right? We have let's make this table here on the right? Let's say we have a number A, right, and it's A0, B0, B0, A1, A0, B, A1, right? And then the number B, right, the ones place is represented by B0, and then the twos place is represented by B1, right? Okay, and we want the outputs, right? So this is going to be A1, A0, B1, B0, and we're trying to add these numbers together, right? And this is going to be carry out 1, carry out 2, right? Since these are empty, they're always going to be 0, right? Okay, so remember, this is a exclusive OR between them, right? Okay, so we have an exclusive OR gate here, so let's use this, okay? So we make this input A0 and this input B0, okay? And that allows us to accomplish this operation, okay? But remember, right, that operation has to be passed to right, one of the outputs somehow, okay? In fact, if we look up here, right, so this input here, right, has to go into an exclusive OR gate and an AND gate, okay? So what I'm going to do, I'm just going to have this output here go to one of the exclusive, I want it to go here, right? So what I'm going to do is I'm going to connect this dot here by sticking a chopstick in there or whatever. I don't know, some sort of metal probably, not chopstick, okay? I also want this output to go to an AND gate, right? Specifically, I want it to go to the second one, right? Right, so I'm going to do this, I'm going to go up here and connect this wire also, okay? Now I have this step, right? Notice I'm flipping up and down, right? So now I made both of these connection here, right? Check here, okay? Right? Well, these inputs also go to the AND gates, right? So what I can do, right, is also just make this my input, right? Just connect them together, right? Anything external I can set, right, by just connecting voltages to it. Okay. The output of this AND gate, where does it go? The output of this AND gate, right, goes to an OR gate, right? In this case, is that what I want? Yeah. Right. Oh, there's a few wires missing. Okay, that's what I need. There's some wires over here also. That's what I need to make that connection. Okay. I want it to go to an OR gate. So therefore, in order to connect this with this, right, what I need to do is to make a wire connection here, and let's make it over here. Okay. So now, right, I'm going to draw in red where the wire connections are. Okay. Going like this, right. This one's going up this, going like this, like this. Okay. Right. Just by punching, you know, connecting those crossing points, right, I can make wire connections. Okay. Right. Similarly, okay, I want the A1, B1 to be here, right? Same thing. So that's my second bit, right? Right. So if I make this connection over here, similarly the way I did this up here, I did this, I skip one, I make it down here, right? Now I connect the output of this exclusive OR gates, right, to these inputs here. Okay? Okay. Right? Then this third output, this third OR gates, right? If I make this, oops, that was red, green here, right? I make it over here, then I do the same thing, right? Because that's what I want to build up my full adders, right? But now I need to connect these two full adders together, right? Because this is basically full adder number one, this is basically full adder number two, right? Okay. In order to connect them together, right, I need to make this connection up here, right? So I'm going to connect this to, right, my regular OR gate, okay? And I want this output here to connect to my other inputs, which goes over here, okay? Right? So now we deal with all the internal connections, okay? So remember what this is, right? If you look at your diagram for your full adder, that's if this is bit zero's input, right? The input of bit zero goes to here, right? Or the ones place goes to here. What should be the answer here? L0, yeah. Okay. Okay. Similarly, this will be L1, okay, right? And then I think there's going to be the carry out from over here, which will go to L2. Sorry, I think this is L. This one, yeah, this one is L2, and this is the carry out 2. Okay, right? And this way, by just connecting wires at the right spot, it allows you to basically build a full adder without connecting any wires. Technically, I didn't do any wiring. I just kind of connected things together. Okay, and the idea of this is called a field programmable gate array because it's an array of dots that you're going to connect, right? Imagine that, right? You just have a matrix of places I want this connection here, right? So let's say you're thinking about it from the top, right? I want this connection here, I want this connection here, I want this connection here, right? All these can be number, right? This might be 0, 0. This will be, I don't know, 2, 0, right? This will be, 4, 5, whatever that placement is, right? It's just an array of places where you want connected, not connected, right? Yeah.
Some of those inputs are not connected to anything.
Right. So some of the well the in so all the inputs here are not connected. Oh, maybe you're thinking about this one?
Yeah, those ones.
Yeah. So what is this up here, right? If we go back to our diagram up here, what is the input for the second OR gate in our full adder? What is the one of the inputs here should be?
Carry in.
It's the carry in, right? But what's the carry in for for the ones place?
0.
Right. So it should always be ground. Okay.
The other ones,
These guys, like where?
the AND gate, only the second term was connected.
Oh yeah. Did I do that wrong? So, so the second terminal for the AND gate. So this AND gate, right, is connected to here. Oh yeah, so that should be connected to the output of the first AND gate, and then, oh, that's also going to be carried in. Yeah. So this should be, this will also be grounded. Okay. Yeah. Sorry. Okay. And then similarly, the second one, oh, the second one, this second one will be actually the carry in from the first bit. Okay. So there are wires that you have to kind of go around, but it does have the functionality to do that. Okay. Yeah. Thinks that's a good catch. Okay. Okay. So so that's sort of the idea of these field programmable gate arrays, where you just connect different these cross wires at different places. Okay. And this is where what we're going to do. So all of you guys should have one of these BASIS boards. So open that up, right? So just take it out. I try not to touch the top part, right? I just try to touch the edge of it, okay? Because there are active components, especially if it's on, okay? Right? So in the middle there, if you look at the picture up here, right? In here, blue on blue is not good, right? In the middle here, this is the FPGA chip, okay? Okay. Inside here are all those gates that I drew and all the possible wire connections that you can have, okay? In fact, it has 32,000 of these wires connections possible, okay? Okay. Um, and essentially, in order to run the FPGA, that's all you need, okay? Well, you need a power supply, right? And that's it. These boards are nice because it's designed for you guys to learn on, okay? So on top of this, on top of just the chip, you also have a bunch of switches, right? So in the current lab, you've been dealing with installing switches. So these switches are built into the board itself, okay? It also have a bunch of LED outputs. I'll show you that in a second when I do a demonstration of that. Okay, so just like the LED on your breadboard, it can display binary information. Okay, in fact, the cool thing about this, it actually has a binary to decimal converter here, so it can actually display those numbers in decimal for you, so you don't have to do all the calculations all the time. Okay, not only is decimal, it also display hexadecimal, but let's not deal with hexadecimal. Okay. Um, okay, so what we're gonna do is we're gonna basically do anything that's more than, let's say, 20 wires, maybe actually maybe like 38 wires on this instead. Okay, because I think I'm gonna have you guys build a 2-bit by 2-bit full adder in the next lab. Okay, that requires about 38 wires. Okay, okay, but after that you don't have to. Well, you could if you want to build more complicated systems. Okay, um, so in the documents on on Canvas, it should have basically a description of this entire thing. So I'm not going to go through all of it. Um, but I just want to highlight that, okay, in order to program an FPGA, you need an FPGA programmer. Hopefully that makes sense. Okay. And in this class, we're going to use this language called Verilog. Okay. Okay. And Verilog is basically the language that Xilinx, this company called Xilinx, written. It's basically well, now it's been like taken over by AMD. Okay. Um, if you were to do this in industry, maybe you will use this other language called Verilog. It's also called Verilog, hardware description language. Okay, VHDL. That's why people say VHDL instead of whatever I just said. Okay, and this is mostly run by Intel. So you can see the divide of the industry here already. Okay, so if you go work for AMD, you will use Verilog. If you go work for Intel, you would use VHDL instead. They're very similar to each other. If you know one, you can just do the other, just with simple syntax changes. Okay. Okay. Um, so in lab 9, okay, you're gonna go through step by step on how to set up this, how to start using it. But all the software called Vivado is installed on these computers in front of you, okay, which is okay. They're slow computers, and if you just program FPGA, it's not too bad. If you want to install it on your own computer, okay, that way you don't have to deal with these. Okay. By the way, these computers have no internet access either, so whenever you want information in and out of it, you have to go through the thumb drive. Okay. If you want to install Verilog, sorry, not Verilog, the Verilog programming language in your computer, okay, it does require Windows, so you cannot do it on the Mac. Okay. And it's about 5 GB of storage. Okay, so Lab 9, there's actually a part, I think Part B, the optional Part B of Lab 9, is like 7 pages of instruction on how to install it. So if you want to install it yourself and not have to deal with these computers, you have to do this over a weekend. Okay, it's going to take you maybe like a couple of hours to deal with it. Okay, because it's just click download something and then wait and then install. It's just time consuming. Okay, but you can do other stuff at the same time. So if you don't want to deal with these local computers, right, install it yourself. Okay, and there's instruction on how to install it, and we're using this specific version from 2018. um, the reason we don't update to 2019 or 2023 is because then we have to change all the instructions all the time. And these software changes like on a monthly basis, right? Because there's no new development in programming FPGAs because, right, this is stuff that we use every day in order to, run our oscilloscope, run our computer, drive our car, turn on lights, right? Um, so, um, so this is going to be, we're using a specific version so the pictures looks the same. Okay, otherwise the menu, a lot of times what happens is that the menu just get moved around different places and stuff like that. Okay. Okay, so what I want to do is I'm going to show you guys how to create a project on Vivado and what that looks like. Find my converter thing here. Since this tablet is super slow, I think it should run fine actually. It's not too bad, but I already have it set up on my laptop, so let's just run the demo here. Okay, so in that case, I should end the recording here, right? Because you're not going to be able to see the screen anymore.